Okay, section 11.5 from Barnett is about implicit differentiation. So we have a couple goals for today. That's to use special functional notation and to carry out implicit differentiation. That's what we're going to focus on in this section. Well, so far in this class, the equation of a curve has always been specified in the form y equals x squared minus 5x, or f of x equals x squared minus 5x, just for an example. This is called an explicit form. Y is given as a function of x. That's what classifies the explicit form, or that's what defines it, rather. However, graphs can also be specified by equations of the form capital F of x and y, two variables, equals to 0. Such an example would be f of xy equals x squared plus 4xy minus 3y squared plus 7. This function is defined by both x and y variables. This is called an implicit form. You may or may not be able to solve this for y. You may not be necessarily able to isolate y by itself on one side of the equation. So we're going to deal with these functions in the section. So consider the equation y equals x squared minus 5x. Briefly back to explicit differentiation. To compute the equation of a tangent line, we use the derivative y prime equals 2x minus 5, and that's explicitly differentiating, so we call the process explicit differentiation. We could also rewrite the original equation as such: x squared minus 5x minus y equals to 0. All we did was subtracted y from both sides of the equation, right? That's all we did here. Well, we can then calculate the derivative of y from that, where we have both x and y in play. This is called implicit differentiation because we're differentiating implicitly in terms of the both, with having both variables, but still in terms of x. Okay, so let's take a look at an example. Consider the equation x squared minus y minus 5x equals to 0. We'll now differentiate both sides of the equation with respect to x, and keep in mind that y is supposed to be a function of x. That's the key to implicit differentiation. You should always remember that even though you're differentiating both sides with respect to x of this equation, one of the variables involved, namely y in this case, happens to be y, is a function of x itself. Keep that in mind. And we know that the answer we're supposed to get is 2x minus 5, but let's double check our work. So we differentiate both sides of the equation with respect to x. On the right hand side, the derivative with respect to x of a constant is just 0, so we get 0. On the left hand side, let's do this term by term. The derivative of x squared is 2x. That's okay. The derivative of negative y, however, is negative dy dx. Why? Because y is a function of x. So when I take the derivative with respect to x, this y is some function of x. So it's going to have a derivative with respect to x. So when I say derive negative y, the derivative is just negative dy dx. Negative 5x, the derivative of that with respect to x is negative 5. So that's how I obtain 2x minus dy over dx minus 5 equals 0. So move the 2x, move the negative dy dx to the other side, and you get dy dx equals 2x minus 5, which is the same as y prime. And that's the same answer we got earlier explicitly. Okay? So I hope you understand how this technique works. This was just to illustrate it, right? It was a very easy example. We're going to use it on things that are more complicated like this. So we're going to differentiate this implicitly. So we start once again by taking the derivative on both sides with respect to 0. On the left hand side, that's the same as taking the derivative with respect to x of each one of these terms. Okay? On the right hand side, once again, we get 0. Well, the derivative of x squared with respect to x is 2x. The derivative of 3xy with respect to x, notice we have to use the product rule for that. I'll do it on the side here just to show you what I mean. I'm going to pick the first function to be 3x, and I'm going to pick the second function to be y. Remember, y is a function of x. That's why it makes sense to say this is the second function with respect to x from the product rule, 3xy. Then the derivative of this is 3, and the derivative of this is just y prime, or you could put dy dx if you prefer, whatever notation you like better. Right? Because this is a function of x. When I take the derivative here, I get y prime. I write the derivative of y with respect to x. Then, by the product rule, this is f times s prime plus f prime times s. So I get 3x times the derivative, which is y prime, plus f prime, which is 3, times the second function, which is y. So really, I get two different things here, and since I had the negative side out front from this derivative, I should apply the negative sign here as well, and I get negative 3xy prime minus 3y. That's exactly how this part of the equation, that step, came to be. It's as a result of the product rule and implicit differentiation. Finally, the derivative with respect to x of 4y, the very last part here, that's just 4y prime, once again. Then, we're ready to solve for dy dx, or y prime, by isolating it by itself on one side of the equation. So grab these two terms, because they contain a y prime, put them on one side, and move everything else to the other side. Okay? And then you could factor out a y prime, and you get 4 minus 3x. Right? Or 3x minus 4 y prime as well is what they got here. Let me show you on the side what happened. So we have negative 3x y prime plus 4y prime equals negative 2x plus 3y. Right? I moved 2x and negative 3y to the other side. But then we're going to multiply both sides by negative 1 just to change the sign so that they match the solution here. No other reason, really. 2x minus 3y. Factor out a y prime, and you're left with 3x minus 4 y prime equals 2x minus 3y. So to solve for y prime, all you have to do is divide both sides by 3x minus 4. That's how this answer was obtained. So that's implicit differentiation. Okay, and here are the steps for the next part, which is to find the equation of a tangent line. So now that we know how to find the derivatives of these functions, we could also talk about equations of tangent lines. Okay, so here are the steps for the same equation. Let's consider that and find the equation at the point 1, comma negative 1. The first step is to confirm that this is a point on the graph. And in fact, it is, because when you plug in 1 for x and negative 1 for y, you end up getting 0. The equation is satisfied. Thus, this step is completed. The second step is to use the derivative from example 2 to find the slope of the tangent. Well, the derivative we got in step 2, y prime, happened to be 2x minus 3y all over 3x minus 4. Right? If you remember, that's what we obtained here. 2x minus 3y over 3x minus 4. So, plug in x equal to 1 and y equal to negative 1 into this expression, and that gives you the slope of the tangent line, because y prime is equivalent to the slope of the tangent line. And that's how we obtain negative 5 as the answer, so that's our slope. Finally, we use the point slope formula for the tangent in order to get our equation. Remember, that's y minus y1 equals m times x minus x1. So this becomes y minus negative 1 equals negative 5x minus 1, right? Once again, using these values to plug in for x1 and y1. And that's how we get the equation of the line to be negative 5x plus 4. So you could apply this implicit differentiation process to do derivatives and find equations of tangent lines. Let's do one more. Consider x e to the x plus ln of y minus 3y, and let's differentiate implicitly. We want to find the derivative implicitly here. Well, let's do it. Differentiate both sides of the equation with respect to x. Right? So I'm going to write out that step here. Minus 3. I can take out the constant since it's a constant, right? It's a constant multiple of a function. So I could write it this way. Well, what's the derivative of x times e to the x? That's a good one. We'll do it on the side. That's a product rule, right? This is the first function. This is the second function. So f of x equals to x. The derivative of that is just 1. And s of x is equal e to the x. The derivative of that is itself, e to the x. Thus, the derivative with respect to x of x times e to the x is the first times the derivative of the second plus the derivative of the first times the second. That gives me x times e to the x plus 1 times e to the x. Or it just gives me x e to the x plus 1. So this is x e to the x, excuse me, I should have factored out the e to the x there. So this is e to the x, x plus 1. Let's make sure we do this right, huh? So this is going to be e to the x, x plus 1. Then we have the derivative of ln of y. Well, the derivative of ln of y is going to be 1 over y times y prime by the chain rule. That's what's involved here. Because y is a function of x, I have to apply the chain rule. Finally, the derivative of y is just going to be y prime. The derivative of 0 is 0. Isolate all the terms that have y prime, that's these two. So we're going to get 1 over y times y prime minus 3y prime equals negative e to the x times x plus 1. Factor out this y prime to get 1 over y minus 3 equals negative e to the x times x plus 1. And that gives us that y prime is equal to negative e to the x, x plus 1, all over 1y minus 3. Right? And we could simplify this a little more by doing some arithmetic and algebra with the negatives there, but that's the answer. Negative x e to the x minus e to the x. They didn't factor like I did here. 3 plus 1 over y. And there we have it. So finally, why are we interested in this implicit differentiation? Well, why don't we just solve for y in terms of x and differentiate directly? Once again, the answer is that there are many equations of this form with two variables, x and y, that are either difficult or impossible to solve for y explicitly in terms of x. So to find y prime under these conditions, we differentiate implicitly. Also, observe the derivative with respect to x of y is y prime, whereas the derivative with respect to x of x is just 1. That was the key fact used in this lecture.